Good afternoon, everyone. Last session of the day. I hope you're all happy that we made it to this far. My name is Oded. I work at VMware Tanzu, which is a business unit focused on all things cloud native and open source. Among other things, we developed the Spring framework, which I'm sure many of you are familiar with, along with things like RabbitMQ, Kubernetes, contributions, etc. Now, as part of VMware Tanzu, we always run this State of Spring on Kubernetes survey every year. And in the past year, what we've learned is that the amount of activity of Spring on Kubernetes has increased from around 44% to 57%, which means that as we go along within the use, I'm sure this year's survey will even make it higher. So we've kind of seen this trend where everything goes to Kubernetes at some point, and it becomes a very important topic of consideration for our developers. So, when we develop for Kubernetes, there are two things we need to consider. The first one is to build the image and how to make sure that it is built correctly. And the second one is to run the image on Kubernetes itself. So let's take each one of them separately and discuss some of the considerations that we have to think about. Number one, there's like a TLDR short recommendation list. First one, prefer using glibc-based kernels, things like Ubuntu, Debian, Red Hat Enterprise Linux, PhotonOS, whatever it may be. Muscle-based libraries, which Alpine uses, has only been supported in the JDK since JDK 16. So it's probably best to stick to glibc for the time being until it becomes more mainstream. In general, it's always preferred to stick to the open source, and the Adapt OpenJDK project, which is now called the Adoptium project, is definitely one of the options you should consider. Or a supported flavors such as Bellsoft, Azul, etc. And of course, you should always try to use the latest long-term support that you can, which is currently Java 17, and 21 is going to be the next one. Now, this is not just for features, right? This is also for actual performance implications. So here's the famous Spring Pet Clinic application. And the boot time on a JVM based on Java 11 takes around 9 seconds to boot up. The same application on the same machine takes around 7.4 when you use Java 17. So this is like 1.5 seconds of startup you're getting for free just by upgrading the JVM. Now, I'm sure many of you are probably still here. Who is still using Java 8, by the way? Just, ouch, yeah. You're not alone. I mean, this is definitely a reality for our industry. In fact, Jerry Rebel did a survey recently where they concluded that around 37% of the companies out there are still using Java 8 and are considering to go to a later version sometime in the near future, but it's a journey. It's not very easy to do. So when you're using Java 8 in production on a containerized environment, there are important things you need to take care of. The most important one is use an update version of Java 8 that is container aware, that is 191 or later. Because if you use an earlier version, like update 130 or 132, you're going to basically get the wrong parameters to your container. The JVM will think, oh my God, I have the entire host CPU and memory that I can use to bootstrap my application. And this is obviously a very, very bad idea that can create a lot of problems for you. For example, here I'm running JDK 8 update 131, and my application thinks, hey, great, I have 4 gigabytes of memory, and I'm going to use 4 cores of my application. While in fact, I just requested 2 CPUs and around 256 megabytes of memory. If I'm jumping to update 292, I get the correct parameters as expected, right? So make sure you use the correct parameters here. Next up, let's talk about writing the Docker file itself. So who really writes Docker files, by the way, just to make sure if I understand when you're building up your images. Okay, so this is like a classic example of a Docker file. You'll even find it still on spring.io if you Google for it. And this will work. I mean, obviously, this is going to boot and it's going to perform, but I highly recommend against it. The main reason I recommend against it is, in practice, what you're doing is you're taking this huge 150 megabyte jar file, and you're basically creating a separate layer for it in your Docker image, right? At VMware Tanzu, we all love make jar not war, as my t-shirt clearly states, but for containers, it's probably a better idea to explode the jar into its own layers to make sure it performs better. So we can actually use Spring itself. Spring has a command called jar mod equals layer tools, and you can give it a command extract, and it will actually unzip, in a way, your jar file into the correct layers, and then you can take each one of these layers and put them in a separate Docker layer. So your final Docker image is going to be highly optimized. So for example, here you can see the dependencies folder, which contains all of the various jar files that count for the dependencies of Spring and other third-party frameworks. And this is my application code, which is like 5 kilobytes of code probably. And this is probably what I'm changing every time I'm making a new build, right? I rarely change the actual dependencies themselves. I don't want to pull to my Kubernetes cluster 150 megabytes every time I make a code change. So here's a better option of a Docker file where you have basically a multi-stage build. You begin by exploding the jar file into separate folders, and then in the second stage, you create the final run image with each one of these layers separately. So again, this also has performance implications. So the same application with the Uber jar, or the fed jar as we call it, takes around 7.2 seconds to boot, while the exploded jar only takes about 5.7. So we improve the boot time even more. And every time you make these optimizations, it has huge benefits when you're working at scale. So avoid using the Uber jars and use the built-in layer tools when you can. Now let's talk about the JVM configuration. So the JVM, as you know, has a lot of defaults for basically everything you do. If you don't give your own parameters, it will have defaults for the garbage collection, for the heap size, for the thread pools, basically everything you can imagine. I highly recommend not to give the JVM too much leeway here, not even if it's just a Spring application, if it's just a standard Java application, because this can create a lot of problems for you. I highly recommend changing these using the Java tool options environment variable and make your own definitions. Now, what should you set for these environment variables at boot time? Well, you can use something like the Java memory calculator. This is a project that started at the Cloud Foundry ecosystem and is still used very well even today. It basically gives you, give me what you know, I'll give you what I recommend at the other end, right? So for example, here I know that I have a container that is going to take 1 gigabyte of memory, and I'm going to have 750 classes, and I'm going to have a stack size of 1 megabyte, and I'm going to have 100 threads, more or less, in my application. So with these parameters, the recommended heap size from the memory calculator is 670 megabytes. Now let's say I need to introduce another Tomcat into my application, which takes another 200 threads. Well, now, because each thread takes more from the heap, suddenly my heap size is down to 470, okay? And if I'm changing things that are related to direct memory, if I'm using NewIO, Kafka, all of these applications that really take memory not from the heap, but from the non-heap memory, then now I can change that parameter because the tool can never understand in general how it's done. So I'm going to say, I'm going to use, after profiling, around 64 megabytes of direct memory. So now my recommendation is 410 megabytes for runtime for the heap itself, which is probably low. Maybe I should consider increasing my container memory at this point, right? So, profile your application, very important. There are multiple options to do that. Avoid the defaults when you can, and set explicit memory arguments. The Java memory calculator is a great option for that. Now it is 2022, and I hope you don't compile your own kernels today for Linux. And I would argue that you don't really have to write your own Docker files anymore when you develop your cloud-native applications, right? So Docker images are great, or OCI images as we call them. They are immutable, they run everywhere, they're self-contained, they can run on my laptop, in Kubernetes, in my data center, wherever it may be. But Docker files are kind of a mixed bag, because it's easy to get started, obviously. You have precise control of what goes into the image, and you control the entire stack from the base image all the way up to the application code. But this also means that you control the entire stack. And when you control the entire stack, it means that you are in charge of everything from CVE patching to performance to optimizations, whatever it may be, you have to take care of it. And, you know, when standards are set by people and not platforms, this can create a big problem. Now, there are multiple projects in the ecosystem to solve that. Jib is a very popular one from Google that basically takes source code in Java and turns it into a container image. But I would highly recommend considering the Cloud Native Build Packs project, mainly because it is a CNCF standard. It's been battle tested in production for years. There are millions of these containers running in production today. And one of its major benefits is really that it has proactive CVE patching. This basically means every time you make a new build, you get the latest CVE patches for your base image, for your OpenJDK, all of these components that you really don't want to control in your day-to-day. You want to focus on your actual application, right? And because it's a standard or a specification, it has multiple solutions. It has solutions based on Kubernetes like KPAC, Google Cloud Run supports it, and it also works as a Spring Boot plugin. So you can simply run Maven Spring Boot build image, and you're going to get a production-ready image at the other side. Now, again, as you can see here, when I'm booting an application that was built with Cloud Native Build Packs, I'm actually getting the memory calculator on startup automatically. So as I start up, the application is going to check, okay, let me check how much memory I have, how much CPU I have, and it's going to set that for me automatically, so I don't have to make sure to set this correctly each time I deploy my application. So this is another benefit that you get out of the box. Okay, so we spoke a lot about building the image. Let's talk about running the image. So when we're running the image in Kubernetes, there's really one important question that you have to ask. Okay, can you restart your application gracefully and make sure that the application restart exactly as you expected? Right? There are many other considerations, but this is by far the most important one when you run in a distributed, chaotic environment like Kubernetes. In order to do that, there are two parameters you have to set, which is the liveness and readiness probes, which are part of the Kubernetes deployment mechanism. And for Spring, we have the actuator project, which lets us expose multiple metrics about our application, about its health. And we can use that to set the liveness probe and the readiness probe for the application. So we can set port 8080/actuator/health. This will be our endpoint to make sure that the application returns a 200 OK. But, as always, there are problems. So let's see what they are. Do you really want to restart your application every time the actuator returns a false information? Right? So imagine, for example, that the actuator endpoints check for your database health or your RabbitMQ health or whatever you're connected to, and it's going to return false every time there's an error somewhere in that ecosystem. You probably don't want to restart the pod every time that happens, right? Because maybe the database just has a hiccup, whatever it may be. Or maybe if you restart the application, you're going to create a cascading failure of just more and more connection pools hitting the database. So it's probably best to keep the actuator endpoint a bit more lightweight, right? Also, it's usually recommended to keep the actuator endpoints in their own separate management port, because you don't want to expose all of this security information into the main application port where everyone can access it. So if I'm putting my application on 8080 and my management port on 1990, now I have another problem because the health is going to be returned from a different port. Maybe my main application is actually not healthy, but my management port returns 200 OK. Another problem I have to take care of. Luckily, we have a solution for that, starting with 2.3 in Spring, where we can basically have our own separate endpoint for the readiness and the liveness in Kubernetes. So now we can basically use the /health/readiness and /liveness in order to make sure that it works correctly. And it doesn't do by default any external dependency checks, right? Just like we wanted. You can override it if you'd like, but by default, it only returns, yeah, I'm alive, all good. Now, starting in 2.6, we also have this additional parameter, which basically allows us to set additional paths beyond the original port that we're using. So the readiness and the liveness probe can also be hosted on the main application 8080 port. And that way, we're going to have basically an entire application all pointing to the main application port, doesn't check any of the background processes, and now we're good to go, and our application reports the correct metadata as we expected. So use Spring's built-in readiness and liveness health probes, keep the probes on the main application port is definitely a good idea, and use a separate management port for all the other metrics and sensitive data that you might expose from your application. Let's talk about graceful shutdown. So by default, even today, when you run a Spring application and you send it a SIG term, your application will just terminate immediately, right? You basically stop working and the application will be down, and in-flight requests are just going to be terminated in flight. Probably not what you want to do in a Kubernetes environment. Now in 2.3 and later, we have this parameter called server.shutdown equals graceful. And what this does is basically tells the JVM to stop the world when it gets the sig term for a predefined few seconds, which you can override with this shutdown parameter. And this basically allows you some breathing room, some 20 seconds or so, where you can allow the application to process the in-flight requests, make sure they are answered correctly, and only then the shutdown process will begin, which is great. Now, Kubernetes is a distributed system. It has a lot of moving parts. It has the API server and the load balancers and pods and deployments and whatever it may be. So you probably want to take some time to wait before you actually start the shutdown process. You basically want to make sure all the components are in sync. I'm not going to send any more requests to this pod that is about to shut down. So you can use a pre-stop hook in order to basically run like a sleep command of like 10 seconds, as I'm doing here. And there's another parameter called termination grace period seconds, which basically says how long should you wait before you just kill the pod and not wait for any other communication from it. So we have like 3 parameters that you have to think about here. The first one is the pre-stop, which basically waits for the 10 seconds in our case, before it begins the actual sig term. Then the Kubernetes sends the sig term to our pod. Next up, our pod receives the signal and begins the shutdown process, right, to the amount of time that it waits based on the timeout per shutdown phase parameter. And on the other side, we also have that termination grace period seconds parameter. The important thing to know here is that the termination grace periods value has to be higher than the sum of the pre-stop and the timeout per shutdown phase. Otherwise, your pods will just be killed 24/7, and you won't even understand why that is, okay? Now, here's the bad news. The default for termination is 30 seconds, and the default for timeout is also 30 seconds. Congratulations, you will always kill your pods unless you change the defaults, okay? So make sure you set the parameters correctly, otherwise you're gonna get a lot of sick kills for your pods. Okay, so use the graceful shutdown setting and make sure the shutdown timeouts are set correctly. Next up is CPU requests and limits. So, as we mentioned before, the JVM makes a lot of assumptions based on the available CPU and memory that it has from the container environment, which is basically how many processors do I have available. Now, in Kubernetes, a CPU request is based on millicores. 1,000 millicores translates to 1 virtual CPU. And a CPU request, when you make your deployment, has nothing to do with performance. All it says is, what is the resource allocation you're allowing me to have? Okay? CPU limits, on the other hand, talks about how much your workload can be utilized before you start being throttled. Basically, it can impact performance, because if you reach the CPU limit, you're going to get slower performance every time. So what should be the values here? Well, based on this actual excellent blog post from robusta.dev, this is a very recommended procedure in the Kubernetes ecosystem in general. Set the CPU request to what you actually need, but never set the CPU limits, right? It might make sense to set CPU limits if you're in a performance test environment where you want to make sure that everything works as expected. But in production, if you have available capacity that no one asked for, why wouldn't you just want to use it and just spike to whatever you can do on that node, right? You don't impact any other processes because the request is the guaranteed value, right? And obviously never go to production without setting both, because then it's basically the wild, wild west, right? So this is actually another recommendation from Tim Hawkins, one of the original founders of Kubernetes in Google, and he also says to never set CPU limits unless, of course, it makes sense. Asterisk here, if you're using things like Google Autopilot, they will always set the limits for you, no matter what you define in your deployment channel. So there are some caveats here based on your managed Kubernetes environment that you have to check. This might change in the future based on some responses on Twitter. So just set your CPU request to, like here, 2,000 millicores or 2 vCPU, and you're good to go. Now, as always, there are problems. Things keep changing in the JVM, and nothing stands still. And here's a recent feature request or even a bug report from the JDK community, where it basically says, actually, we shouldn't use the request to define the available CPU and memory. We now want to use the CPU limits to do that. Didn't we just say this is probably not a good idea? Now let's understand again what is the reason here. So as I mentioned, the CPU request is the guaranteed value, right? So this means if I have a node with 16 cores, and I'm going to start deploying an application to it, so at first I'm going to request 4,000 millicores of CPU, and the result is that I'm actually going to get the entire 16 cores, right? Because this is what I requested, this is the minimum value, but nothing else works on that node at the moment, which means that I can basically use the entire node. So I get 16 CPUs. Get active processors will return 16. Now another container comes into the picture. It also wants 4,000 millicores. It joins the same node. Now each one of them actually gets 8 cores. Get active processors becomes 8, right? And whenever you add additional cores, additional containers, that number is going to change. Basically what it means is that the value of get runtime, that get available processors, will drift over time. So the JVM can never really use that parameter to understand how to properly set the values for the JVM. Goes back to what I said before. Do not let the JVM make assumptions with defaults. So you can solve that, but just an asterisk here. If you just don't define anything, the default is 1,000 millicores, and there's a bug right now where it's again going to take the entire host. The host CPU here, so again, don't use the defaults because it can create havoc. So to solve it, just set the active process account yourself. Okay, just don't let the JVM make these assumptions without you telling him exactly what you want. You can say, I request 2 vCPUs from my deployment, and I want 4 active processors from my JVM, and it will honor that, right? So if it spikes and suddenly has available capacity, it will use that available memory, that available CPU. But whenever it goes back down to the initial setup, then it will use less. So just make sure you have active configuration in your JVM. Okay, last up, memory requests and limits. So, unlike CPU, which is, as you can say, a compressed resource, right? So you can throttle it and basically say, I'm going to give you less capacity at that time. A memory is not like that, right? A memory, if you request more than you are allowed, and then it's going to need that memory for other workloads, you're basically going to get a problem because you cannot really scale back the memory without restarting the pod. Okay, so if you want to avoid that issue, just always make sure that the memory requests and limits are set to the exact same value. That way you always avoid the option of just getting your JVM or your pod to be restarted without you understanding why that happened. So here's again the full picture. You set the correct amount for memory, the correct amount for the CPU. Do not set the CPU limit, set the active process account, and you're good to go. So putting it all together, this is from my colleague, Adib Saikali, which has a very good summary for basically most of what I said right now. So a good starting point for JVM workloads is to scale up before scaling out. Not talking about resilience, of course. Set like 2 vCPUs and 2 gigabytes of RAM. Set active process account yourself. Set the JVM memory settings the same for request and limit. And you're good to go, right? And do not set CPU limits. That's basically all you have to do to get a good starting point for your application after profiling it correctly. Now, looking ahead, this is obviously all recommendations based on what we have today at the end of 2022. Spring Boot 3 was just released this week. Actually, Spring Framework 6 was just released this week, and Spring Boot 3 is going to be released next week. And it has built-in support for GraalVM, which means that many of these recommendations could easily change based on the new changes in the future. Things like Project Laden and static images, Project Crack, which creates image snapshots, Project Loom with virtual threads that was also mentioned in these sessions. All of these can really impact the recommendation, and you have to make sure that you're with the community to make sure that you're aligned. So just a very quick example. If I were to boot a Docker image based on Spring Boot 3 with GraalVM, so the build time will take a little while. It takes around 3 minutes. but the startup time for the Spring Pet Clinic application, which is quite large, is around 0.05 seconds. It's like immediate, right? You have instant boot time for your Spring-based application, which is quite incredible. If you're interested in reading article form of this talk, I have this session. This is the blog, and this is a direct link to the article itself. You're welcome to read it. There are more things that are related to Spring Cloud and more considerations that go beyond these initials. Thank you very much. I'm here if you have any questions, and enjoy the rest of the day.